Hi, I'm Serge. I work for Rivos. We've had some broad tours and introductions to the generally accelerators, how they can benefit Velox. So my hope with this lightning talk is to, in a brief, overgeneralized fashion, but nevertheless dig down into some of the technical detail that might be involved in supporting a workload, the kinds of design engineering decisions that would have to be made. So I will recap on the kinds of CPU bottlenecks that we observe in the Apache gluten, this is a Spark gluten Velox stack. So what kind of shape devices SIMT accelerators are, what kinds of challenges they present, and then how that translates into actually accelerating a bottleneck workload. So what do we see when we look at where time is spent in TPCH queries? We've seen variations of this breakdown earlier at VeloxCon. Where time is spent depends very much on what we are doing. Nevertheless, some common patterns emerge. We see large blocks of time spent moving data around, decoding, encoding, compressing, decompressing. We see large blocks of time spent partitioning, hashing. We see large blocks of time spent in calculated columns. So some of these things are better fits for accelerators than others. Calculated columns, generally there's a long tail of complex functions. However, frequently they are embarrassingly parallel things. The cells depend on values from the row that they're in and not much else. So what kinds of things are we talking about when we talk about SIMT accelerators? So these are devices capable of executing multiple threads. The threads run in lockstep, so they're all executing the same instruction at the same time. If you reach a control flow decision, if you reach a branch, then some of the threads become disabled. You do one side, you disable those threads, re-enable the other half. You do the other side, you've serialized your execution. Generally, there are facilities to help with context switching. So you have more than one warp's worth of threads. You can rapidly switch between them. This is to help hide latency. There is generally some facility for dedicated I/O for transferring moving bytes around. So this can happen asynchronously with respect to both what the core is doing and with the host. There is generally some small amount of shared memory that all of the threads have access to and can use to communicate with each other. You have many of these cores in the accelerator, so you have potentially a very large amount of parallelism available to you. There is high bandwidth memory, much higher bandwidth than you're going to get with DDR on the host. Generally, you are going to have, so the device won't have access to the host memory, host won't have access to the device memory. You're going to have to use the dedicated I/O to move data back and forth. With some accelerators, you do have unified memory. There may be a performance or other penalty involved with using that, because the whatever facilities you have for dedicated I/O are asynchronous, it is still better overall to use those where available. So what kind of challenges do we hit? Data movement, communication between the threads within the warp. Generally, you have hardware to assist you with that. You have instructions that cause things to synchronize and propagate information between the threads. Between warps, some accelerators will give you hardware support with that. For others, at wider scale, it's going to have to go via memory using atomics. So thread scheduling, this is the biggie. You get control flow divergence if different threads make different control flow decisions. So in the worst case, all of your 31 threads deconverge, you end up serializing everything. So you end up essentially single-threaded, even though you've got a warp's worth of threads potentially available. Finally, there are overheads involved in scheduling the work, and there are overheads involved in moving data back and forth between the host and the device. So, as I mentioned earlier, some of the bottlenecks fit this better than others. If something is embarrassingly parallel, it's great. Each thread just does its own thing. You can do everything in lockstep, different offset. It all transfers nicely. Of the bottlenecks that I picked on earlier, data compression looks like the single worst possible fit for this. Fundamentally, with data compression, the problem is that every piece of work you do depends on all of the previous work that you've done. It's not at all obvious how to parallelize that. Nevertheless, there are things we can do. So what are we talking about when we talk about data compression? So for this space, for the columnar formats that we are likely to encounter, we can mainly focus on the LZ77, LZSS algorithm family. So what we can think of the compressed data stream as a series of instructions to copy bytes, either directly from the compressed data stream or from earlier in what we've output previously, or from a dictionary, depending on the format we're using. So some compressed formats, we've thrown everything under the bus except performance. And in this case, that is literally what we have. Snappy LZ4, that's literally what the compressed data is. For others, you can stick an entropy coding stage on the end of that. So you can have a Huffman coder or an arithmetic coder. And then you end up with Z standard or with deflate or with something from that family of algorithms. From the compressor's point of view, though, what you are doing is the same thing in a loop over the input. You look at the next few input bytes. You look them up in the compressor's dictionary. If you hit a match, you emit an instruction to copy from either dictionary or previous output, depending on your compression algorithm. If you don't hit a match, you emit an instruction to insert that byte. That sequence is a literal. Either way, you update your dictionary and you keep going. So how on earth do we parallelize that? The initial step is to break the input up into blocks. Generally, the data compression algorithm will have some means of doing that. For Snappy LZ4, that family, there is a native block size, and the spec guarantees that you won't reference data outside of that block, which means you can encode blocks in parallel, independently of each other, and then gather the results. For the more complex algorithms, there is generally a framing format that you can use to the same effect. So what that gives us is one block per core in our accelerator. So one of our 32 threads in our warp is doing useful work. The others are idle. Implementation is trivial. We do get some performance win, some small modest performance win over doing the same thing on CPU. We're leaving a lot of performance on the table. Can we do better? We can. So there are a number of possible things we can do. We can think of the compressor as a state machine. If we think of the algorithm earlier, at any given time, it's in one of just a few possible states. It's either scanning the input, or it's emitting instructions, or it's updating the dictionary. So we can refactor it that way. We can have a switch statement in a loop, whatever hints the accelerator needs to cause threads to reconverge at the end of that, branchless code within each case. So at any given time, a significant portion of the threads within our core will be in the same state. We can throw a block at every thread instead of a block at every core. And suddenly, if we have enough data, we get a somewhat bigger win. So it is still not amazing. It's maybe a factor of 8, factor of 10 win over just doing one block per core. Because of the some of the threads will be in one of the other states with respect to whatever's currently executing, and also you've introduced a synchronization at the end of every loop iteration. However, that is an approach that can be taken, and also it means for the same amount of data, you can get some parallelism out even with one core, and then if you have useful work for the rest of your accelerator to be doing, maybe whatever's generating the data, that can happen at the same time. So an alternative would be cooperative SIMT. The core could be all 32 threads in your warp doing exactly the same operation in lockstep with exactly the same arguments, except for some parts of the operation. You can have each thread work on different data, synchronize, and select what happens next based on the results, which then need to be broadcast to all the threads in the warp. There are hardware instructions in pretty much every accelerator to assist with this. And so what does this look like? For instance, for the scan through the input data, every thread could be, rather than one thread checking one offset, then going on to the next, then going on to the next, you could have 32 threads check 32 different offsets, perform the dictionary lookups, gather the results. If there is a match, you can work out which threads hit a match, and therefore where to begin emitting the copy instruction. So depending on the particulars of the accelerator, other parts of the algorithm can be accelerated the same way. So depending on whether it can coalesce writes across threads or what kind of granularity you have on memory bank conflicts, that kind of detail. You can, for instance, do cooperative memory copies or for the literals, or even cooperatively emit the instructions. It's been a bit of a whirlwind tour. What kinds of things can we get? NVIDIA have a big table of results for NVComp, which is a closed source data compression library that they provide. It actually used to be open source a few versions ago, and at that time they were using this strategy for Snappy. We don't know what they use now, however, they do hit fairly big wins compared to doing the same operation on CPU. So in summary, accelerators are wonderful for embarrassingly parallel workloads. However, even if your workload is not that shape, if there is one thing you take away from my presentation today, it's still possible, absolutely possible, to get a win by offloading it to an accelerator with a bit of engineering effort. So going forward, as Ori explained earlier, Wave will be providing a common framework for collaboration. The hope is that lots of people will be contributing, helping contribute kernels and other things to Wave. We intend to be open sourcing some of our work in this space in the coming months as things become stabilize and become available. Please keep an eye on GitHub for future developments. Thank you.